Robots and automated machines have always been a part of spaceflight, ever since the world's most famous one, Sputnik, ushered humanity into the era of space exploration, and to this day, they are an integral part of people's presence in space. Every gram launched into space is very expensive, and when humans are part of the payload, these expenses accrue significantly. In addition to the cost of the payload arriving to low Earth orbit, the time spent there is incredibly costly as well. So governments and the taxpayers that fund these space programs demand that the people sent to space are as productive as possible. Therefore, it makes sense to provide those spacefaring employees with robots to help them do their jobs better. Designing and manufacturing robots for space has no shortage of challenges. Like most robots anywhere, but to a stronger degree, they must reliably function smoothly without the need of serious repairs, must be useful for a unique set of needs, and be lightweight for low-cost transport. The challenges specifically for space are numerous as well. They must operate in zero gravity, handle the gravitational equivalent forces of liftoff, and protect from the radiation of space once it reaches orbit. Despite these difficulties, engineers and space agencies continue to try to overcome them. Today, on the International Space Station, humankind's most consistent destination in space, many technologies have been proposed, like surgical robots for emergencies to save lives doing procedures that can't wait for a return to Earth. Instead of the robotic Canadarm, which swivels from a stationary base, a robotic arm on a rail could access and repair all parts of any space station's interior, including the Tiangong space station operated by the People's Republic of China. The Russian Federation's Skybot F-850, the world's second humanoid robot in space, arrived to the International Space Station in 2019. Though developed for the purpose of replacing humans on spacewalks, it was only able to plug cables together and return to Earth that same year. A bold attempt at robotics on the ISS was spearheaded by the United States National Aeronautics Space Administration, or NASA, with Robonaut 2. With its two five-fingered hands, torso, backpack, and golden helmet, it was a semi-autonomous humanoid machine designed to work alongside astronauts. NASA and the Defense Advanced Research Projects Agency, or DARPA, worked with General Motors to design, manufacture, and test the Robonaut and Robonaut 2 at Johnson Space Center in Houston, Texas. A staple for PowerPoint presentations and internet clickbait, the short-lived Robonaut prototype stayed on Earth for development. As the Robonaut 2 arrived to the International Space Station in 2011, it generated a flurry of excitement upon being presented to the public and successfully completing a series of tests. However, after faulty wiring caused the robot to be inoperable, it ultimately failed to provide consistent and useful labor-saving service for the crew on the International Space Station and returned to Earth in 2014. The most successful robot helper to date is the semi-autonomous Astrobee project, executed by NASA, which has been assisting the crew of the International Space Station since 2017. The three cube-shaped Astrobees, Honey, Bumble, and Queen, maneuver freely in the zero-gravity environment. They use fans, sensors, and cameras to give real-time data to ground control, and despite having received much less fanfare, are by all accounts a resounding success. In this video, we will investigate the aspects of the development, accomplishments, and failures of these two projects in their attempt to fulfill one of science fiction's oldest and most consistent tropes: robots working alongside people in space. In order to develop the most prominent feature of the Robonaut, its humanoid hands, researchers had to develop a range of sensory processing routines for the robot to do tasks that a 6-year-old human could do with ease, such as push a button or turn a screw. The robot's vision system, referred to as the visual cortex, had to be capable of depth perception, scale, orientation, and yield a binary profile of objects of interest. It was first programmed to recognize hand tools from a variety of angles via silhouette templates. It then assigned each item a level of confidence, and after being aware of what it could identify, was able to execute the command to pick up the tool by name. The machine had to be programmed to probe in an exploratory procedure and have a reflexive grab on the proper tool or handrail at an appropriate strength of grip. It had to orient the tool in a proper manner and not move in a way that might damage the very expensive apparatus. Unfortunately, it was very difficult for the Robonaut to identify items that were not spatially isolated. Upon arrival and installation aboard the ISS, Robonaut 2 was able to successfully sign Hello World in American Sign Language, execute simple tasks of button pushing, the first handshake between a human and a robot in space, and a brief demonstration of cleaning an air filter. Tragically, a ground wire improperly jeopardized the mission. The electronics were damaged in a way that was too difficult and complicated for the crew members to accomplish with their limited tools and capabilities orbiting 17,500 miles per hour around the planet. The robot was returned to Earth, and a new prototype, Valkyrie, is in the works for further investigation of humanoid robotic assistance to astronauts. For the Astrobee project, engineers at the Ames Research Center had to develop an entirely new method of travel using air fans for maneuverability in zero gravity. Engineers were able to provide it maneuvering capabilities so the robot could travel to any part of the space station and perform a series of automated tasks. Working autonomously or via remote control by astronauts or ground control, the robots were designed to complete tasks such as taking inventory, documenting experiments conducted by astronauts, and finding disturbances. The mobility is made possible specifically by two impellers on either side of the Astrobee that pressurize interior plenums that provide airflow to 12 exterior nozzles that are present on every single face of the free flyer, resulting in 6 degrees of freedom holonomic control. There are two propulsion modules, one on each side of the vehicle. In case those fans break down, however, the robots would be unable to move, so a need arose to devise an alternative method for maneuverability. NASA has a novel strategy to get the most out of the Astrobees now that they are already on board the International Space Station. They utilize every opportunity to invite innovation from the public, academia, and internally. Students can download Astrobee software from the website GitHub and write an experiment with different programs. In one case, a postgraduate thesis resulted in a proof of concept on board the International Space Station. It began when experiments were conducted at the Naval Postgraduate School in California to give these machines the capability to maneuver like people do, by pushing, coasting, and landing to another location in the station's interior. Researchers constructed a replica of the machines with robotic arms and grippers and then simulated zero gravity on a two-dimensional surface. A granite monolith was leveled, and compressed air allowed the devices to operate in a virtually frictionless environment. Several iterations of the machines were rendered to provide the best conditions. Cameras around the monolith worked in tandem with the processing unit to allow the machine to have situational awareness. As the project became more advanced, it transitioned to another phase where testing was done in a simulated interior of the International Space Station at the Ames Research Center. This time, all computation and processing was done inside the unit itself, and after a series of experiments, the data was transferred to the team for analysis. Ultimately, the results from both labs were conflicting, with discrepancies possibly being attributed to differences between the units and air-bearing malfunctions affecting the data. However, a subsequent study repeated the experiment and was able to get more repeatable results. A successful self-toss maneuver was defined if the Astrobee was able to travel in a concise, consistent trajectory greater than 30 centimeters over the initial 50 seconds from gripper release, without impacting anything during the initial 50 seconds of the maneuver. Thankfully, researchers were able to continue studying these maneuvers in the actual microgravity conditions on board the International Space Station. They unfortunately were unable to get repeatable results that resulted in the units propelling themselves to the exact same place every time. It was found that the observed momentary increase in angular speed of the active Astrobee prior to release could be attributed to a change in the center of rotation of the active Astrobee, as it rotates about its proximal joint prior to release and rotates about its center of mass after release.